Hi, I'm Sala, and in this video we'll discuss how to compute the Laplace transform of a single sine pulse that appears in the figure. Let us first write the time domain expression of that pulse. Signals are assumed to be 0 for negative times, at least in unilateral Laplace transform. Then we have the sinusoid during a given time, just a half period, associated to frequency omega in radians per second. And then after that half period, then the function of time we are dealing with is again identically 0. In order to have, numbers to plot things, we will assume that we are dealing with 50 Hz signals, so a half period of that frequency corresponds to 10 milliseconds. And this semi-period 0.01. So to plot it with the symbolic toolbox, this will be the sinusoid, but that sinusoid lasts forever, and then we will multiply that sinusoid by a couple of Heaviside functions, step functions. The Heaviside function is 1 for non-negative arguments and 0 for negative ones, so Heaviside of t is just the unit step at instant 0, so it makes everything at negative time to disappear, so the sinusoidal fragments for negative times will disappear after multiplication by Heaviside t, and this semi-period minus t will end up being, when used as an input to the Heaviside function, will end up building a reverse step so that it will be 1 for times before 0.01 and then 0 afterwards, because indeed when time is greater than semi-period, then this argument to Heaviside is negative, so the output of Heaviside is 0, and then this construction is the way to build a piecewise function in the symbolic toolbox that is 0 outside of the interval, starting at 0 and ending at 0.01. So good, once we have this u of t, we can plot that function of time with fplot, and here we have the input pulse whose Laplace transform we wish to compute. How can we compute that? Well, Matlab's Symbolic Toolbox knows how to do it. So if I ask which is the Laplace transform of that u, we get this. Of course, our goal is understanding how this expression arises if we were asked for it in a pencil and paper examination. We will carry out the Laplace transform in two ways. So let's start with the recommended one, which is via the concept of delay and superpositions and linearity of the Laplace transform. We will show that the input is the superposition of two waveforms. A first waveform u1, which is the sinusoidal from time 0 onwards, and a second signal u2, which is the same sinusoidal but delayed a half period. So u2 would have this expression, and the way to write it in the symbolic toolbox is just replacing t by t minus semi-period in this Heaviside sinus. Indeed, we will plot the sum of u1 plus u2 in a very thick line, and then u1 and u2 independently in a thinner line. Let's analyze what we got. We see that the sum of the red and yellow lines is the blue one. The blue one is the sinusoidal pulse we wish to deal with. And of course, if we add to a sinusoidal, the red one, the same sinusoidal but displaced 1/2 period, then the yellow line is 180 degrees out of phase with the red one, so they add up 0, and that happens from 0.01 onwards. So the idea for Laplace transform will be that if I can compute the Laplace transform of the red thing, which of course I can because it's in tables, it's sinusoidal, so its Laplace transform will be omega divided by s squared plus omega squared. And if I can compute the Laplace transform of the yellow line, which of course I can because it's a delayed sinusoid, so it will be the same thing times the delay operator, delaying 0.01 seconds, then the Laplace transform of the sinusoidal pulse will be the sum of these two things. So this is it. By first method, let us do it with the symbolic toolbox, but the idea is clear. We just need to add these two things to get the Laplace transform of the blue waveform. This is the Laplace transform of the whole sinusoid starting at 0. This is the Laplace transform of the delayed sinusoid, and then the sum of them. The denominator is exactly the same, and the numerator, well, the difference is that we have 1 in here and the delay term down there. So 1 plus this exponential coincides with the output of the Laplace command. So this is the computation by method 1, by delay and linearity superposition. A second way of computing the Laplace transform would be applying the Laplace transform definition just directly, but I flag it as a non-recommended because usually straightforward manipulations from things in Laplace transform tables are faster to carry out than this integration stuff. But okay, let's go with it. The Laplace transform of a signal is this integral by definition. And in this case, as our signal ends at time 0.01, we can forget about infinity and stop integration at 0.01. Well, good, so we need to compute this. How is it done? Well, we'll integrate by parts. Copying this to here, the integration by parts is kind of this. And then if I name u the exponential and dv the sinusoid dt, here we have u and v, the integral of the sinusoid is minus cosine divided by the frequency, and in here we have v and du. So with some manipulations, the evaluation of this thing at time equals 0, cosine is 1, and in a semi-period, cosine is minus 1, so you can check we get this thing in the right, and then as the Laplace variable s can get out of the integral because we are integrating with respect to time, and we have 3 minus signs, we end up writing the integral in here as this stuff here, where capital V of s is the integral in there, exponential times cosine. So good, we have the first integration by parts. If we do the same with that v function, then again, if u is the exponential and dv is the cosine dt, then the integral of the cosine is the sine, divided by, of course, the omega frequency, and the integration by parts is this thing, so we can work out things. And as the sinusoid at 0 is 0 and that the semi-period is also 0, then this thing vanishes, gets to 0, and this other stuff, again, taking s out of the integral, and as I have two negative signs, then I get a positive term here, and this stuff ends up being this thing where u of s is this integral, the Laplace transform we are actually evaluating. So we have done integration by parts twice. As this was v of s, I can replace it here, and if I make it slightly small, u of s is equal to this factor, and then replacing this here, and moving all this in there, I get s squared over omega squared u of s. So we are now ready to end our transform computation by just solving for u of s. If I multiply this expression by omega squared in both sides, I get this, and then moving this to the other side of the equality and dividing, we get the final same result as with method 1 or as with the Laplace command of the symbolic toolbox. So this is it. In this video, we compute the Laplace transform of the blue sinusoidal pulse in 3 ways. First one, by just believing Matlab's symbolic toolbox. Second way, by realizing that the blue thing is the superposition of a red sinusoidal and a delayed sinusoidal in yellow. And third option, by computing this thing, integrating by parts. The 3 ways give us the same result as intuitively expected. So we end the video here. Thanks for your attention.